Have you ever wondered how scientists know what distant stars are made of? We can't travel millions of kilometers into space to collect samples. Yet, astronomers can determine the elements present in stars simply by studying the light they emit. The answer lies in one of the most fascinating properties of atoms. In this video, we will explore the science behind atomic spectra. First, we need to understand what light actually is. Light is a form of electromagnetic radiation. Although it appears in many different colors, each color is simply a light with a different wavelength. Red light has a longer wavelength while violet light has a shorter wavelength. Another important property of light is its frequency, which tells us how many waves pass a point every second. Wavelength and frequency are related by the equation C is equal to lambda f. Light also behaves as though it is made up of many tiny packets of energy called photons. The energy carried by each photon depends on its frequency and is given by E is equal to hf, which can also be written like this. When white light passes through a prism, it spreads out into a continuous band of colors ranging from red to violet. This band of colors is called as continuous spectrum because it contains every visible wavelength without any gaps. However, not every source of light produces a continuous spectrum. If instead of sunlight we observe light emitted by a heated gas such as hydrogen, the result looks completely different. Rather than seeing a smooth rainbow of colors, we observe only a few bright colored lines separated by dark regions. This is known as an emission spectrum. There is also a third type called an absorption spectrum. Imagine white light passing through a cooler gas before reaching a prism. Instead of producing a complete rainbow, certain colors are missing, appearing as dark lines. These missing wavelengths correspond to the light that has been absorbed by the atoms in the gas. Every element produces its own unique pattern of spectral lines, almost like a fingerprint. To understand why atoms emit or absorb only certain wavelengths of light, we need to take a closer look inside the atom. An atom consists of a small positively charged nucleus surrounded by electrons. Electrons in an atom are restricted to specific energy levels. They cannot exist at energy levels between these allowed levels. This idea is one of the fundamental principles of quantum mechanics. The lowest possible energy level is called the ground state. If an electron gains energy by heating the atom or passing electric current or in any other way, it can jump to a higher energy level. This is known as the excited state. However, excited states are very unstable, and after a short time, the electron returns to its lower energy level. And when it does, the excess energy is released as a photon. And the energy of the emitted photon is exactly equal to the difference between the two energy levels. This simple idea explains why atoms emit only certain colors of light. We already know that the energy of a photon is given by this formula. This means that every possible photon energy corresponds to a specific wavelength or frequency and therefore a specific color. Since electrons can only occupy certain energy levels, they can only make certain transitions between those levels. As a result, they can only emit photons with specific energies. And because each photon energy corresponds to a particular wavelength, atoms emit only certain colors of light. This is why we observe bright spectral lines instead of a continuous rainbow. The same idea also explains absorption spectra. When a white light passes through a gas, atoms absorb only those photons whose energies exactly match the difference between the two allowed energy levels. The remaining wavelengths pass through unchanged, leaving behind dark lines in the spectrum. Every atom has its own unique arrangement of energy levels, and as a result, emits and absorbs a unique set of wavelengths, giving it its own characteristic spectrum. By studying the spectral lines produced by an element, scientists can identify it with remarkable accuracy. This technique is widely used in chemistry, physics, and material science, but an interesting application also exists in astronomy. By studying the light passing through or emitted by a planet's atmosphere, scientists can identify the gases present. Detecting molecules such as water vapor, oxygen, methane, or carbon dioxide helps us understand whether that world might be capable of supporting life. By analyzing the light from distant stars, astronomers can determine the elements they contain without ever visiting them. Every bright or dark line in a spectrum is a clue that tells us something about an object that may be billions of kilometers away.